In lecture 2, we're going to talk about resonance and Lewis acids and bases. Now, this is a couple topics that you've probably, again, been familiar with for a little while. Usually, resonance is something that you learn about in general chemistry, and you've probably also learned a little bit, at least, about the definitions of Lewis acids and bases. But we're going to spend a lot of time in this course using resonance as a tool to understand chemistry. And turns out that most chemical reactions in organic chemistry can be classified or viewed as a Lewis acid base reaction. So, whereas in general chemistry, you probably spent more time using Bronsted-Lowry acids and bases, and again, although you learned about Lewis acids and bases, you probably didn't use them much. In most of this material, the focus is going to be on viewing the chemical reactions as Lewis acids and bases. So, the subtitle to this chapter is Was Lewis Correct? Meaning, we've spent a bit of time talking about Lewis theory and Lewis structures, and resonance structures, resonance theory kind of plays into that. But we're going to start looking at more complicated structures that maybe suggest that the picture that Lewis presented us in his theory was maybe a little bit too simplistic. So we're going to dive into the realm of lore, meaning material that has been passed down more as a method of teaching and understanding than as a basis in fact. So this is a pretty interesting topic chapter. There's quite a bit of philosophy to it. So hopefully that'll keep it interesting. Basically, Lewis structures and Lewis theory is founded on being able to predict a structure simply based on the number of valence electrons that we have. When we go through and take a molecular formula and try to draw a Lewis structure for it, the first step that we do is to add up the valence electrons for all the atoms involved and use those as kind of a bookkeeping method so that we can keep track of how many bonds we can have, how many lone pairs we can have, etc. So ideally, from number of valence electrons, something very simple, something easy to understand, easy to calculate, we would ideally like to predict, first of all, constitution. Now, what do I mean by constitution? I mean how everything is connected. The fundamental kind of skeleton of the molecule is the constitution of the molecule. Beyond constitution, once we understand how everything is connected, we'd like to know structure. So how is constitution different than structure? When I say structure, I mean things like bond lengths, distances between atoms, angles of structures, angles of bonds, maybe rotation of bonds, how flexible or floppy or rigid is a molecule. That's aspects of structure that beyond constitution would probably be nice to know about. Furthermore, charge distribution. So where are our charges located? If we have charges, do we not have charges? Maybe do we have partial charges? Is the electron density in the molecule distributed equally, or is it asymmetrical? Again, like we saw in our previous chapter, charge distribution, looking at formal charges or looking at dipoles or electronegativity, can serve as a map to identify hot spots where reactions might occur. So if we could get charge distribution simply from valence electrons, that would be pretty awesome. Furthermore, energy content, if we could somehow know what the strengths of bonds are, if they're strong or weak, if they're reactive or unreactive, how they're likely to break. Are they likely to break symmetrically or asymmetrically? That would be nice to know. And taking all these four properties into account, combine them in some way to, again, understand reactivity. That would be pretty nice. Now, for these last four, Lewis notation, Lewis theory, Lewis structures fails in at least some aspect to predict these properties. Lewis is very good at getting us constitution. It really helps us put together a molecule in a way that makes logical sense and does in a fundamental way represent reality. But it fails in a lot of ways, and at least some aspects, like we say, to give us structure, to predict distances or angles, to understand charge distribution, energy content, and reactivity. So we need a better theory. Now, to understand the shortcomings of Lewis theory, I want to present you with a pretty interesting example here and drive home the difference between equilibrium, which again is a reaction that has a forward pathway and a reverse pathway, and resonance, which is two or more different ways to draw electron distribution around a constitutional skeleton of a molecule. So here's an interesting structure, HC triple bond NO, and I've gone through and I've placed formal charges where they belong. We've got a nitrogen with 4 bonds and no lone pairs. That's a positive charge. We've got an oxygen with 1 bond and 3 lone pairs. That's a negative charge. So as this stands, we can assess the stability or reactivity of the molecule by first of all looking at the octet rule. Does every atom have an octet? And indeed it does. The hydrogen's got its duet, I guess you'd say. Carbon's got 4 bonds, that's 8 electrons. Nitrogen's got 4 bonds, that's 8 electrons. Oxygen's got 1 bond and 3 lone pairs. That's 8 electrons. So we're good there. Now, unfortunately, we do have charge separation, meaning that we have formal charges. We have charge that are separated rather than being combined and therefore neutral. Basically, we've got a positive charge on the nitrogen and a negative charge on an oxygen. And if we have a choice between having no charge separation or having some charge separation, we'd prefer to have no charge separation. We'd like to have the molecule be as evenly distributed in electron density as possible. So that's not such a good thing. Now, we can fix this problem, okay? Notice that oxygen, as drawn here, has 1 bond and 3 lone pairs, and that gives it a negative charge. But recall from last lecture that neutral oxygen wants 2 bonds and 2 lone pairs. So if by some means we could take one of these lone pairs and turn it into a bond, so move it from being purely in oxygen's domain and instead have them being shared between oxygen and nitrogen, then oxygen would have 2 lone pairs left over and 2 bonds, and therefore it would be neutral. So by shifting this lone pair to make it into a bond, we can eliminate the negative charge. We can fix that negative charge on oxygen. Now, there's a problem with that. Do you see what it is? If we move this lone pair and make it a bond from nitrogen to oxygen, we are now giving nitrogen a 5th bond. That means nitrogen would have 10 electrons in a valence shell that only has 4 orbitals. So we would be violating the octet rule for nitrogen. So that's a bit of a problem, but again, we can fix it. The way we can fix it is we can take one of the bonds in the triple bond between carbon and nitrogen and move it on to carbon as a lone pair. So when we do that, we get this structure, okay? We now have a neutral oxygen with 2 bonds and 2 lone pairs. We still have 4 bonds to nitrogen. So nitrogen now still has its octet, but it does still have a positive charge. But carbon, instead of having 4 bonds, as in the first structure, now has 3 bonds and a lone pair. So we still have all of our octets in this new structure. That's a good thing. By rearranging these bonds, we still maintain all of our octets. That's great. Unfortunately, we still have charge separation, right? We've still got a positive charge and a negative charge. That's not great. We haven't really fixed anything in that respect. Unfortunately, we do now have the negative charge in a less ideal site. Now, what do I mean by that, and how do I know that? Well, think about electronegativity. How happy are these atoms to have a negative charge? Oxygen is more electronegative than carbon, meaning that oxygen would rather have negative charge than carbon would. So we now have a poorer site for the negative charge on carbon rather than oxygen. Let's think about the geometric implication of this redistribution of electrons. Just based on an analysis of charge localization, the top structure has a better electron distribution with the negative charge on the O. The second structure has a worse electron distribution with the negative charge on the carbon. But I've also done something a little bit sneaky with the bond lengths. Did you catch that? If you look at the bond lengths here, the single bonds are very long, the triple bond is very short, and the double bonds are somewhere in between the length of the single bond and the triple bond. That is factually true. The length of the bond is inversely proportional to the number of electrons that you have, meaning that if there are 2 electrons in the bond, it's going to be very long. If there are 4 electrons in the bond, it's going to be shorter. And if there are 6 electrons in the bond, it's going to be shorter again. So when we change a single bond between between nitrogen and oxygen into a double bond, and we change the triple bond between carbon and nitrogen into a double bond, we are changing the geometry of this molecule, right? In the top structure, nitrogen is closer to carbon than it is to oxygen. In the bottom structure, nitrogen is approximately midway between carbon and oxygen. We'll just assume for now that a carbon-nitrogen double bond is about the same distance as a nitrogen-oxygen double bond. So we are not only changing the electron distribution, but we're also changing the position of the atoms here. Now, if we were to plot the energy of the molecule on our y-axis as a function of the nitrogen's position, meaning it's either on the left in the top structure or it's in the middle about midway in the bottom structure, it would look something like this, right? We have lower energy when the nitrogen is towards the left in the top structure, and as we move it towards the middle, the energy goes up. We end up with the negative charge in the wrong position. So what I've drawn here is a double minimum, right? We've got a global minimum down here, but we've also got another local minimum up here. We've got 2 minima, and in chemistry, that means that we have 2 real structures. So we have a structure here, and as we move the nitrogen over, we get to a new structure. And the double minimum implies that you can move between those 2 structures from one structure to the other, from one structure to the other, right? Back and forth. As long as we have enough energy to get over this little hump, we could move that nitrogen from one position to the next by moving the electrons from oxygen over to the carbon. Now, that may be true. That may be a picture of reality. But in fact, the real energy diagram looks like this. There is not 2 structures for HCNO. There is only one structure for HCNO, and you'll notice that that one structure, that single minimum, has the nitrogen somewhere between the left position, where we have a triple bond, and the midway position, where we have a double bond. That is the difference between resonance and equilibrium. In equilibrium, we have two structures where we can interconvert one structure to the other, going back and forth. There's a forward pathway and a reverse pathway. In resonance, there's only one structure. Now, what I mean by this is the bond length between the carbon and the nitrogen is not really a triple bond, and it's not really a double bond. It's somewhere between the two. That is the idea with resonance. It's a very important idea with resonance, is that the real structure, the picture that the molecule actually looks like, is somewhere between the resonance structures. Usually it's the case that neither resonance structure, whether you've got two structures or 10 resonance structures, none of the resonance structures fully accurately captures what the real structure looks like. The real structure is some combination of the two. So it becomes a little bit of a puzzle then to try to understand, when do we have equilibrium? What does equilibrium look like in a molecule versus resonance? What does resonance look like in a molecule? So here I'm giving you a couple structures where we have two pairs that look fairly similar. We've got this structure on the left compared to this structure on the right. If you look at this, this is fairly similar. We've got a hydrogen connected to a carbon that is single bonded to an oxygen, single bonded to an H, and the carbon is also double bonded to an O. On the structure on the right, we've got a similar thing where we've got a hydrogen connected to a carbon with a single bonded O and a single bonded H, and also on the carbon is a double bonded O. Now, if you look at these molecules, you'll say, well, these are the same, right? All we have to do to convert one structure on the left to the structure on the right is just flip the molecule over, and you have identical structures. But for my argument here, I wanted you to think about these atoms as, although they are indistinguishable because they're both oxygens, as being distinct from one another. So oxygen A versus oxygen B. And if you look at the molecule that way, they are quite different, right? The difference between the structure on the left and the structure on the right is that we're changing carbon's bond to oxygen A from being a single bond to a double bond, and we're changing the carbon's bond to B to be a double bond to a single bond. And we're also moving the hydrogen. Instead of it being attached to oxygen A, we are moving it to oxygen B. So those are very different structures then. We are not only rearranging the electron distribution, we're not only changing where the electrons are, we're also physically disconnecting this hydrogen from oxygen A and moving it to oxygen B. Now, on the structure below, it's a little bit different. Instead of having that hydrogen attached to A, we have a single unpaired electron on A. And in the structure on the right, we have moved that single electron onto B. And concomitantly with that, we're changing the single bond from C to oxygen A into a double bond, and we're changing the double bond from C to oxygen B into a single bond. So, which one of these is equilibrium and which one of these is resonance? That would be a great question. And here's the answer. The top pair are in equilibrium with one another. These are two different species, meaning when the hydrogen is on oxygen A, it's a different molecule from when it's on oxygen B. We are physically breaking bonds and reconnecting them. That type of interconversion is a double minimum type interconversion, and that is equilibrium. meaning it can be influenced using factors that affect Le Chatelier's principle. So anything that you know about equilibrium would apply to this type of a situation on top. On the other hand, the system at the bottom is an example of resonance. These are not two different structures. These are actually the same structure. Now, I did the same trick that I pulled before where I modified the bond lengths. Again, if you pay very close attention, the single bond between the C and the O is longer than the double bond between the C and the O. And if you look at the top situation where we have equilibrium, the carbon bond to oxygen A is long on the left and short on the right. So as we go back and forth between these two double minima, between these two species in the double minima, the bond is actually physically getting longer and shorter as it interconverts from a single bond to a double bond, and as that hydrogen moves from one oxygen to the other. But in resonance, look at here. Notice that the double bond is actually the same length as this single bond. Okay? Meaning as we go from the structure on the left to the structure on the right, the bond lengths are not really changing. Rather than going back and forth between the two, these are just one structure. Remember, equilibrium goes back and forth between two minima. Resonance is just one minimum somewhere between the two structures that we can draw. So we can actually see this using a experimental procedure called electron paramagnetic resonance, that there is only one bond length. There are not two types of bonds here. There is not a carbon-oxygen single bond and a carbon-oxygen double bond where the single bond is long and the double bond is short. In fact, we only have one type of bond, and that one type of bond only has one bond length. There is only one nuclear geometry in this radical species where we have an unpaired electron. There is actually two nuclear geometries when we have the hydrogen there. That's an equilibrium situation. We can also see this using quantum calculations, that when we have the radical, you have one geometry. Now, if we add another electron in here, and now we've got a negative charge, instead of having a neutral radical, we've got a negative charge, we still have the same effect, meaning we still have one nuclear geometry. That negative charge is being spread out between the two oxygens, but these bond lengths are not shifting from being long to short or short to long. And we have evidence for this when it's not a radical, but instead it's an actual negative charge. Rather than using electron paramagnetic resonance, we can now use infrared spectroscopy to see these geometries and see that they are actually, there's only one actual geometry here. We will learn more about spectroscopy in semester 2 of this course. So the choice between resonance and equilibrium really needs to be based on experimental facts or a better theory that can help us distinguish between a single minimum and a double minimum. Meaning, if I were to give you these structures and say, pick which one is resonance and pick which one is equilibrium, you would not be able to use Lewis theory to determine that. There's no way that Lewis would be able to predict this. So in order to determine this, we either need to do an experiment and look at the geometries and see, do we have two geometries that alternate one to the other, in which case it's equilibrium, or do we only see one geometry, in which case it's resonance? Okay. Or we need some better theory, some theory beyond, that's more sophisticated than Lewis theory, that can help us distinguish the single minimum versus the double minimum. Okay, so just to summarize, equilibrium is when we have two real species and we can alternate between the two. There's a pathway that lets us convert from one species to the other, from a reactant to a product. In resonance, we have one real species. There's only one molecule. There's not two. A and B are not different. It's just that there are two reasonable ways to draw them using Lewis theory. Again, Lewis theory doesn't give us a way to draw the real structure. So we have to draw A and we have to draw B using Lewis theory and say, okay, well, the real structure is somewhere between the two. Now, let's go back to VSEPR theory for a moment and see how resonance can affect structure. Again, we saw before that resonance can affect structure by moving the position of that nitrogen, right? If that was equilibrium, that nitrogen would move back and forth. But in resonance, that structure is somewhere between the two. So here we've got three structures, CH4, that's methane. We've got formaldehyde, CH2O, and we've got acetylene, C2H2. Now, looking at the number of entities bound to carbon, 4 things bound to carbon would have a 109.5 degree bond angle. 3 entities bound to carbon would have a 120 degree bond angle. And 2 entities bound to carbon would have a 180 degree bond angle. Okay, so if we look at this structure, this is called acetamide. We'll study molecules similar to acetamide again in the second semester of this course. Let's go through the carbons and identify which bond angle would apply. So for the carbon on the left, what would that bond angle be? How many entities do we have bound to this carbon? Well, we've got 4 entities bound to this carbon. We've got the 3 hydrogens and the carbon in the middle. So that carbon's geometry would be 109.5. The center carbon, how many entities are bound to the center carbon? Well, we've got 3. Again, we've got the O, the C, and the N. So the geometry around that carbon should be 120 degrees. Now, what about nitrogen? How many entities are bound to nitrogen? Your guess is probably 3 because you see hydrogen, hydrogen, and carbon, but be cautioned. Notice that nitrogen doesn't have 8 electrons around it. It doesn't have an octet, nor have I drawn a charge to it. In this structure, nitrogen actually has a lone pair. So be careful about that. Sometimes lone pairs are left off of a structure. For example, here on this oxygen, I've left off the lone pairs. A lot of times chemists are lazy and they omit them just because they assume that anybody reading the structure would be able to interpret that correctly. So this nitrogen, in order to have 8 electrons and no charge, we need to have 3 bonds and a lone pair. So now, rather than thinking, okay, the geometry is going to be 120 because we have 3 entities, we've now got a 4th entity, okay? So what should that be? 109.5, right? You're actually wrong. The actual geometry on this nitrogen is about 112 degrees. Now, what in the world is going on? Well, we've got a resonance structure. What we can do is we can take that lone pair and shift it to make it a bond between the nitrogen and the carbon. Now, in doing so, like we saw before, we would be giving carbon a 5th bond. Carbon's already got 4 bonds, so if we take this lone pair and make it into a new bond, the carbon would have too many bonds. But we can instead, to kind of compensate for that, move one of these double bonds onto oxygen and make it a new lone pair. So now what do we have? Now we have this, where we have 4 bonds to nitrogen and no lone pairs. That gives nitrogen a positive charge. Now carbon still got 4 bonds, so it's neutral, but oxygen would have 1 bond with now 3 lone pairs, which means it's got a negative charge. So we've got 2 structures. Now, in the first structure, like we had here, nitrogen's bond angle should be 109.5. In this structure, nitrogen's bond angle should be 120. We've gone from having 4 entities, the hydrogen, hydrogen, carbon, and lone pair, to 3 entities, just the hydrogen, hydrogen, and the carbon. So here are our resonance structures. Again, 1 at 109.5, 1 at 120. And again, when we have resonance structures, the real structure represents a hybrid of the two. The real structure lies somewhere between the two. Now, 112 is not exactly halfway between 109.5 and 120. In fact, you see 112 actually is a little bit closer to 109.5 than 120. Why would that be? Why would the real structure not be exactly between the two, but look a little more like one than the other? Well, if you look at the structures and think about their relative stability, your conclusion would be that the structure on the right has charge separation and the structure on the left does not. So the structure on the left is a better structure. And as a result, it contributes more to the real picture. If you were to calculate this, 112 is about 23% closer to 109.5 than 120. So we figure that rather than being 50-50 contribution, it's about only 23% contribution of 120 and 77% contribution from the 109.5 structure. So we could draw the quote unquote real structure in this kind of a way. Remember again that the real structure kind of looks like a combination between the two. In one structure, we had a single bond between the nitrogen and the carbon. In the other structure, we had a double bond between the carbon and the nitrogen. So the real structure should be somewhere between a single bond and a double bond. So I'm going to draw a single solid line and a dotted line there to say that we're somewhere between 1 and 2 bonds. The same is true between carbon and oxygen. We're somewhere between 1 bond and 2 bonds. We've also got partial charges. Rather than having a full charge on nitrogen or 0 charge on nitrogen, we've got a partial positive. And instead of having a full charge on oxygen or 0 charge on oxygen, we've got a partial negative. Now, again, it's not half of a charge because there was not equal contribution between the two. And this is not a 1.5 bond. It's somewhere between 1 and 2, but it's not halfway between 1 and 2. So again, Lewis theory, Lewis structures don't give us a great way to accurately represent exactly how much of this bond is single bond character and how much of this is double bond character, or how much of this charge is negative versus neutral, or how much of this charge is positive versus neutral. In the real picture, the electrons are spread out, right? We moved these electrons from the nitrogen to between the nitrogen and the carbon, and the electrons between the carbon and the oxygen onto the oxygen. We've effectively transferred a lone pair from the nitrogen there, and there up to the oxygen. We have what we say delocalized them. We have spread them out. Rather than those electrons being stuck on that nitrogen, they are spread out along this pathway between the nitrogen, carbon, and oxygen. They are delocalized. I'm going to use that term a lot. The point of resonance is to delocalize the structure, to delocalize those electrons. The more charge that you can spread out and distribute between multiple atoms, the better. Neither of these atoms experiences a full charge. They only experience a partial charge, and that's good. Previously, we looked at 2 structures, and we said one was better than the other because of the charge distribution. We had a negative charge on a more electronegative atom, or we had charge distribution versus no charge distribution. And we used that criterion to determine which structure was, say, better, which one was the major contributor. So let's discuss a little bit about how we would choose that in other situations. Here's an example of two structures. Again, this is one molecule with two resonance structures. And let's analyze this and figure out which of the two is the major contributor, which one is going to have more influence on the real structure. Now, to get from the structure on the left to the structure on the right, all we have to do is take one of these bonds between carbon and nitrogen and move it onto the nitrogen to make it, instead of being a bonded pair, being a lone pair. Now, when we do that, we now change the charge. Instead of carbon having 4 bonds, it only has 3 bonds. And so it's 3 bonds with no lone pairs that's got a positive charge. Nitrogen with 4 bonds has a positive charge. If we turn one of those bonds into a lone pair, we have 3 bonds and a lone pair, and its formal charge is 0. So by going from the structure on the left to the structure on the right, we are fixing the charge on nitrogen. We are correcting that and making it neutral. But instead of fixing it, we are also turning the carbon from being neutral into being positive. So based on electronegativity, meaning which atom is going to pull harder on the electrons, is carbon more electronegative or is nitrogen more electronegative? Well, nitrogen is more electronegative, so it would be more likely to win a tug of war. If we were to decide which direction would the electrons want to go based on electronegativity, they would move towards the nitrogen. Okay, so based on that, the structure on the right is a better choice. The structure on the right is the result of moving the electrons onto the nitrogen. What about charge distribution? Which one of these molecules has the charge in the more ideal position? Is it better to have a positive charge on an N, or is it better to have a positive charge on a C? Well, again, you can analyze this based on electronegativity. Nitrogen is more electronegative, meaning it would rather be negative, not positive. Carbon is more electropositive. So which atom would rather have the positive charge? The carbon would. So again, based on charge distribution, the structure on the right is better. What about the octet rule? Which structure, if either of these, satisfies the octet rule for as many atoms as possible? Well, the structure on the left actually satisfies the octet rule for every atom. The hydrogens get their duets. Carbon's got 4 bonds, so it's got 8 electrons. Nitrogen's got 4 bonds, so it's got 8 electrons. The structure on the left satisfies the octet rule. The structure on the right, however, does not. Nitrogen still got its octet, 3 bonds and a lone pair. All the hydrogens have their duets. That's great. But carbon has lost an entire pair. Instead of having a bonding pair, carbon loses that pair altogether, and it only has 6 electrons. So it turns out that the structure on the left is the major contributor. The structure on the right is only a minor contributor. The molecule looks more like the left structure than the right structure. And remember that the right structure was actually better as far as electronegativity was concerned and as far as charge distribution was concerned. So the octet rule wins. The octet rule is a more important factor in determining major contributor versus minor contributor than charge distribution is. So again, the true structure resembles a hybrid or a composite of these two structures, with more influence from the left than from the right. And again, that is because of the octet rule. So you can get more nitty gritty if you want. You can say, well, how much more? Is it 60-40? Is it 70-30? How much more important is the structure on the left than the right? You could also ask, how do we represent this? Okay, these are real problems that we have with notation. And again, a lot of this is post-diction, meaning we might only know this after we do an experiment. We might only be able to come to this conclusion that the octet rule is more important than charge distribution after doing a lot of experiments. There's nothing fundamental about chemistry that says that octet rule satisfying is more important than charge distribution, charge location. Okay. Evaluating this requires a lot of experience, meaning having seen lots of examples, and a little bit of intuition. Okay. There's a lot of qualitative, kind of hand wavy conclusions that we have to make here. So don't worry about that too much. Don't get too stressed out about that. But just do remember that the octet rule is usually more important than a misplaced charge. Now let's look at one more example where we have formaldehyde, CH2O, and a resonance structure for formaldehyde. What we've done is we've taken a bonded pair between the carbon and the oxygen and we're moving it onto the oxygen to make it a lone pair. So now the formal charge on carbon goes from being 0 with 4 bonds and no lone pairs to +1 with 3 bonds and no lone pairs. And the charge on oxygen goes from being neutral, 2 bonds and 2 lone pairs, to negative, 1 bond and 3 lone pairs. Okay, so a quick analysis of these two resonance structures would say that no charge separation is better than charge separation. Having neutral charges is better than having plus and minus charges. And also an octet is better than a non-octet. So carbon having 8 electrons is better than carbon having 4 electrons. So by both of our metrics, looking at charge distribution and looking at octets, the major contributor is going to be the one on the left, and the minor contributor is going to be the one on the right. Now, again, the real structure, the true structure of formaldehyde, resembles a hybrid of all the resonance structures with more contribution from the good structure than from the bad structure. So the real structure should have mostly a double bond, but a little bit of a single bond. And the real structure should have mostly a neutral oxygen, but a little bit of a negative oxygen, and mostly a neutral carbon, but a little bit of a positive carbon. If we draw it like that, where we show a little bit of negative charge on the O and a little bit of a positive charge on the C, well, that's a dipole. The definition of a dipole is separation of charge that's not a full charge, not a full negative, and not a full positive. So what we know about the dipole moment in formaldehyde can be viewed as simply the result, the outcome, the repercussion, if you will, of having two resonance structures. And again, here's the electron potential map of formaldehyde. We've seen this before. It's a surface that shows kind of how dense the electron cloud is. And we've got most of our electron density up top at the oxygen and lower electron density down by the hydrogen and the carbon. This electron potential map mirrors what we would expect if we look at a dipole based on electronegativity, and it mirrors what we would expect if we consider that the real structure is a combination of the two resonance structures. An analogy that I like to use for resonance is this photo analogy. I basically took a photo of a rose and I removed all the blue from the photo. I removed all the red from the photo, and I removed all the green from the photo. And if you look at either of these three photos on top where the color's been removed, no single picture gives you the real picture of the rose. Looking at the picture on the left, you don't get a good picture of the color of the rose. Here, you don't get any sense of the color in the rose. Here, you don't get any sense of the greens. The only way that you get the real picture is if you combine all of these three individual pictures together. The information from the picture on the left, combined with the information from the picture on the right, combined with the information with the picture in the middle, gives you the real picture, okay? That is how resonance works. You can't really know the structure of a molecule unless you consider any and all of the resonance structures in concert with one another and weighting them based on which one should be the major contributor, minor contributor, etc. Right? So, what is so great about these octets? How do we get such a strong influence from structures that have their octets? What's that coming from? Also, a good question would be, how bad are these sextets, right? How bad is it to only have 6 electrons like we do when we have carbon with 3 bonds? How bad is that positive charge? How bad are charges with formal charge separation? How bad is that? And how bad is bad, right? How many atoms have to be missing an octet before the charge separation structure is better than the non-octet structure? Okay, these are great questions. I have a question when drawing these structures. Is it more important to try to fill the octet or to have the lowest formal charge on as many atoms as possible, especially carbon, and why? Okay, these are good questions. These are difficult questions to answer. It's really difficult to formulate a theory or a set of rules to answer these questions in as universal as a way of possible. Now, I found a list of rules for resonance from another textbook. This is not from your textbook, but I thought it was kind of interesting and I want to show it to you. It said rules, empirical rules for assessing the relative importance of the resonance structures of molecules and ions. So the first thing I want to pull out here is empirical. Do you know what empirical means? If you want to look it up, you can. But empirical basically means determined from evidence or determined from experiment. These are rules that we put together by looking at lots and lots and lots of examples. These rules do not come out of any theory, out of any fundamental rules in chemistry. These are just something that we have kind of piecemealed together based on evidence. Okay, so the first rule that this source gave us, it says resonance structures involve no change in the position of nuclei. Only electron distribution is involved, right? We saw that in the very first example, or actually, I think it was the second example, where the hydrogen was moving between oxygen A and oxygen B. When the hydrogen moved, when we moved the nuclei, though that was not resonance, that was equilibrium, right? So resonance structures involve no change in the nuclei, only the electron distribution is changing. Now, I want to clarify that and say it's only our depiction of the electron distribution that's involved. The pictures that we're using, these Lewis structures, that's only our depiction of reality. That's not really what reality looks like. So, second, structures in which all first row atoms have filled octets are generally important. However, resulting formal charges and electronegativity differences can make appropriate non-octet structures comparably important. So they're saying that you may have non-octet structures that have particularly wonderful charge distribution, and that might make them equally as important as other structures that do have filled octets. Third, the more important structures are those involving a minimum of charge separation, particularly those among atoms of comparable electronegativity. So if we have a choice of having no charge distribution no charge separation versus charge separation. Generally speaking, as long as our atoms are similar, we're going to take the one with minimum charge separation. And then it says structures with negative charges assigned to electronegative atoms may also be important. So having a negative charge on an O is pretty good. Having a negative charge on an N is okay. Having a negative charge on a C, not so great. Now look at what they did here. They used words like generally important, however, okay, resulting formal charges and electronegativity differences can make appropriate charges, okay, particularly, okay, may be important. These are weasel words, okay? The book, this source, was trying to put together rules that weren't really rules. They were maybe guidelines at best. Okay. A lot of hand wavy terms here that leave a lot of room for exceptions. Okay. Your book, Wade, has some better rules. They're still a little bit hand wavy, but they are better than that other source. So I'm presenting you those here. So all resonance forms must be valid Lewis structures. You're not allowed to add or remove electrons out of thin air. They have to be as valid as the other structures that correspond to that molecule. Only the placement of the electrons can be shifted from one to the other. So you're not allowed to move nuclei. You're only allowed to move the placement of the electrons. And all electrons should flow in the same direction. When we move electrons, you're always going to move electrons in the same direction. Okay, we already said nuclei cannot be moved. Atoms can't be disconnected or rearranged. You can't change their constitution. The number of unpaired electrons, which we call radicals, must be the same. So if you have one unpaired electron in one structure, you darn well better have one unpaired electron in all of your other structures. Otherwise, you are, again, pulling some electron somewhere out of thin air. Good contributors, again, generally have all octet rules, all octets filled. Again, there's a weasel word there. As many bonds as possible. That helps us have octets, and as little charge separation as possible. Now, charge separation is different than delocalization. Delocalization is when we are moving the electrons from one structure to the other. Charge separation is where we have a negative charge next to a positive charge, or a negative charge a few atoms away from a positive charge. Negative charges are more stable on electronegative atoms. That's stuff that we've talked about before. And resonance stabilization is most important when it serves to delocalize a charge over two or more atoms. When we can have, say, three resonance structures, and a different atom in each structure bears the charge, what that means is each atom bearing the charge actually has about a third of a charge to it. It doesn't get pinned. It doesn't get stuck with that entire negative charge. Instead, all three atoms kind of share that burden. So going back to this from before, hopefully you see now that resonance, when we have one real species that can be represented in two reasonable ways using Lewis theory, is really a failure of simplistic notation. The fact that we have to draw resonance structures in order to capture the real species, what the real structure looks like, is simply because our way of drawing these molecules is too simplistic. Usually, resonance structures that have multiple resonance structures, are unusually stable. That is an interesting kind of coincidence, maybe, that whenever we can draw more combinations of electron distribution, we end up with more stable structures. So we're going to use that a lot as our guide. Remember, the whole kind of overarching goal in organic chemistry is to develop a system of intuition, a way that we can just look at a molecule and understand what it's going to do. If we can look at a molecule and find its resonance structures, the more resonance structures there are, the better molecule it is, the more stable it is, the happier it is. Okay. Now, this is a gold star moment here. Anytime we say something is stable or something is happy, or maybe something is unstable or something is reactive or something is unhappy, you always want to think compared to what? Okay. If I say a molecule is stable, well, what does stable mean? All that it means is that it's more stable than something else. So what are we comparing the molecule to, right? When we say something with some molecule that has resonance structures is unusually stable, compared to what? Well, compared to a molecule that doesn't have resonance structures, okay? Anytime we talk about a kind of property like stability or reactivity, always ask yourself, what are we comparing it to? In what context are we saying something is stable? Okay. An acid, for example, an acid might be stable just sitting in a jar all by itself. But if you bring it in contact with a base, it suddenly becomes extremely reactive. Okay. Or maybe a substance is very stable in a nitrogen atmosphere, but as soon as it comes in contact with some oxygen, it becomes explosive. Okay. So saying something is stable, ask yourself about the context. Maybe not necessarily the environment, but what are we comparing it to? Stable compared to what? Okay, let's take these rules from resonance and figure out why these two structures are resonance forms, meaning that they are two structures, two drawings that represent the same molecule, and why this pair of drawings are not resonance forms. Okay, what is wrong with this drawing that makes it not resonance? And can we figure out what it is? If it's not resonance, what are these? Okay. Now, are both of these valid Lewis structures? It might take you a few minutes to go over them and calculate all the valence electrons and count them up and figure out formal charges. But I'll go ahead and tell you that yes, both of these structures are valid Lewis structures. Both of these structures are valid Lewis structures. So that's not the problem. Okay. Do we have the same number of electrons, same number of atoms, and same number of charges? Yes, we do. We've got 1, 2, 3, 4, 5 hydrogens in both cases, three carbons in both cases, one positive charge. If you count up all the bonds, we have the same number of bonds. The same is true over here. We've got the same number of atoms, same number of each atom type, same number of electrons. That is not the problem. Same charge, it's neutral and neutral. That's not the problem. Do we have any excessive valence? For example, do we have any cases where we accidentally drew 5 bonds to carbon? Again, that would technically be an invalid Lewis structure, but no, we don't. All of these have the correct valences. Okay. Now, carbon has 6 electrons instead of 8. That's allowed. It's not ideal, but it's allowed. It's something like 5 bonds to carbon would not be allowed, but 3 bonds to carbon is fine. No, the reason why this pair over on the right are not resonance structures is because nuclei are moving. Okay. In order to go from this structure on the left to this structure on the right, we have to physically disconnect one of these 3 hydrogens and reconnect it on the left carbon. Okay. Again, yes, you can maybe view this molecule as just being the mirror image of this guy on the right, meaning if you flip them over, they're the same. But if you think about this as being carbon A, carbon B, and carbon C, we are moving a hydrogen from carbon C to carbon A. And that makes them not resonance structures. In these forms over here, we are not moving any of the nuclei. The only thing that is changing is the electron distribution. So these two structures are resonance structures. These two structures are actually different species. They represent the same thing. They are identical species. They are maybe, say, twins. They're identical, but they are individually different things. They have different connectivity of their atoms. Let's go back and spend a little bit more time relating stability to resonance. Okay, I've said in a previous slide that resonance structures tend to be unusually stable, and that being able to delocalize these charges, being able to spread a charge out and move it from one atom to the other by rearranging the electrons, is a good thing. We can kind of spread that burden out among many atoms. So here's acetic acid. And as we know, acetic acid is a Bronsted-Lowry acid, meaning that in water, it will dissociate with one of its hydrogens. Now, we'll learn in a little while why it is the hydrogen on the oxygen that is dissociated and not the hydrogens from the carbon that are dissociated. But if we imagine the dissociation of this hydrogen, the products would be acetate and a hydronium. We're just going to disconnect this bond and transfer the H plus from the acetic acid to the water, right? That's a standard type of Bronsted-Lowry acid reaction. Okay, we get the conjugate base, acetate, and hydronium. Now, that is an equilibrium reaction. We are physically disconnecting this hydrogen. We are reconnecting it to the oxygen and water to make hydronium. This is an equilibrium situation. We have a reactant situation, a reactant context, and a product context, and they are going to have different energies. Okay? It's a double minimum, you might think. Now, there is in fact a resonance structure to acetate, right? If I take the electrons on this negative O, again, we want to fix this negative charge. We want to correct it. And we can correct a negative O by turning one of its lone pairs into a bond. By turning that lone pair, or one of these lone pairs, into a bond, we now have two bonds and two lone pairs, and that oxygen becomes neutral. Now, carbon, again, would be getting a fifth bond. That is not allowed. So at the same time that we bring electrons down to make this into a double bond, we have to move electrons up out of this double bond to get them away from carbon and put them back onto this oxygen. Okay. Notice what we've done. We have physically moved the negative charge from oxygen A down here at the bottom to oxygen B up here at the top. Now, these are identical resonance structures. These are going to be equal contributors. Neither one is better than the other. They've both got a double bond O, a single bond O, with the negative charge on the single bonded O, and then the CH3 group. These are indistinguishable from one another, but they technically have the negative charge on a different oxygen. So that is resonance. It's different from equilibrium, okay? We are not changing the attachment of nuclei. We're not detaching anything by moving these electrons around. All we're doing is delocalizing that charge by rearranging the distribution of the electrons. And that's a good thing, okay? neither one of these oxygens needs to bear the full negative charge. Okay. The real picture, since these are equal contributors, these are equal structures, the real structure would be 50% of the way between these two. So we'd have 1.5 bonds on each carbon oxygen, and we'd have a half of a negative charge on each oxygen. The charge on that oxygen is delocalized, and we say the product is resonance stabilized. It is more stable than it would be if we were unable to delocalize that charge. A stable product, so the fact that the product of this reaction is particularly stable, it's got resonance, indicates that acetic acid is a good acid, okay? It's very likely to give up its H+, because if it does give up its H+, it's going to get a stable product. Acetate is very, very stable. Okay? In fact, the proof of this is that acetic acid is such a good acid that even a base as weak as water will facilitate that transfer. Okay? Water is not a great base. It's neutral, as we know. So if an acid is going to react with water, it's got to be a pretty darn good acid. Carrying that idea forward, if we can look at a conjugate base like we just did with acetate and see that it is a resonance stabilized anion whose charge is delocalized over 2 or more atoms by resonance, that gives us a clue as to the stability of the acid or the reactivity of the acid. Now, let's look at these 3 acids here. This is ethanol, and the pKa of ethanol is 15.9 on a scale of pKa going from around 0 to about 50. It's actually a fairly weak acid. It's still acidic, but it's pretty weak. It's pretty weak as far as acids go. Now, let's think about the conjugate base of ethanol. If we remove this hydrogen as an H+, leave the oxygen with its negative charge from the electrons from that OH bond that we're breaking, we get what's called ethoxide. And ethoxide has no resonance structures. There is no way, no opportunity for us to move this negative charge off of the oxygen. That oxygen is cursed to bear the full burden of that negative charge for all eternity until it gets a hydrogen back, perhaps. Okay. So that's ethanol and ethoxide. Looking at acetic acid, we're going to do the same thing that we did to ethanol. We're going to remove that hydrogen as H+ and dissociate it like a Bronsted-Lowry acid would to get a conjugate base. Now, as we saw, when we remove that hydrogen from acetic acid, we get acetate, and there are 2 resonance structures to acetate. That fact, the fact that the conjugate base is very stable, means that the acid is more reactive. Again, remember, a strong acid produces a weak, stable conjugate base. And if we look at the pKa, we go down from 15.9, about 16, to about 4.75. That is a significant increase in acidity. The increase in acidity, the difference in acidity between ethanol and acetic acid, is due to the fact that the negative charge in acetate can be delocalized, and that makes it much more stable. The stability of acetate means that acetic acid is more likely to give up the H+. We can go further if we look at methane sulfonic acid. This is methane sulfonic acid. The acidic hydrogen on methane sulfonic acid is the one attached to the oxygen, as was the case for acetic acid, and as was the case for ethanol. So if we remove the hydrogen from that oxygen, we get this what's called the methane sulfonate ion. And it turns out that there are 3 resonance structures for methane sulfonate. That negative charge on that O can be delocalized onto the top oxygen, with the other 2 oxygens getting the double bond, or it can be delocalized onto the bottom oxygen, with the top 2 oxygens getting the double bond. So 3 resonance structures means a more stable conjugate base, and therefore a more reactive acid, a stronger acid, and that again is reflected in the pKa of methane sulfonic acid. So going from no resonance structures in the conjugate base to 1 lowered our pKa about 12 pKa units. That's a huge amount. Going from 2 to 3 brings us down about another 4.5, right? So resonance is hugely important in assessing the stability of something, in this case, the stability of a base, a conjugate base, and from that, inferring the reactivity of the acid. The more stable the base, the more reactive the acid. Okay? And in this case, the stability of the base is not coming from the location of the negative charge. Notice that in all cases, the negative charge is on an O. That's not what is determining the difference in stability. What is determining the difference in stability is the degree to which that negative charge can be delocalized, spread out between 2 or more atoms. All right, that's about enough for resonance for today. We're going to finish off this chapter, which is really the second half of chapter 1, by talking about the Lewis definition of the acids and bases. Remember, there are 3 definitions of acids and bases. The first one is the Arrhenius definition. The second one is the Bronsted-Lowry definition. If you're not familiar with those, you can go back and read up on them in the book or in your general chemistry notes. But the third definition, the Lewis acid-base definition, is often kind of swept under the rug in general chemistry, but it's extremely important and useful in organic chemistry. So let's remind ourselves what the Lewis base definition is. The Lewis acid definition is that an acid is a substance that accepts a lone pair of electrons, and a Lewis base is the opposite of that. A Lewis base is a substance that donates a lone pair of electrons. So we are moving beyond the notion of H plus being transferred, right? In Bronsted-Lowry acids and bases, we're always looking at where's the H plus going? What's the donor? What's the acceptor? That kind of thing. In Lewis, we are moving beyond that. And rather than focusing on transferring H pluses, we're going to focus on transferring electrons. And when we do that, we are going to be making and or breaking bonds. Now, almost every chemical reaction that you're ever going to find involves transferring electrons to make or break a bond. So in a lot of ways, the Lewis acid-base definition is a universal definition. You can apply it to almost every reaction that you ever come across. Okay, here's an example of a reaction where we have B, which is going to be our base, and HA, which is going to be our acid. And in this reaction, the base donates a lone pair to the hydrogen. Okay? Don't worry about why it does that for now. Just understand that it does that. And again, we are using this arrow notation to kind of track or diagram the flow of electrons. Okay? So we're going to donate this lone pair from the base to the acid. That again is the definition. The base donates the electrons. The acid accepts the electrons. Now, what is with this second arrow? Okay. Why do we need a second arrow here? Well, remember, hydrogen is only allowed to make one bond. It only really has the one s orbital available to it. So if the hydrogen is going to accept a pair of electrons from the base, it needs to lose the 2 electrons that it already has. So these 2 arrows are actually going to happen simultaneously, where we're basically saying that as the base donates the lone pair to the hydrogen, and as that bond is formed, the bond between the H and the A is broken, and those electrons go from being a bonded pair to being a non-bonded pair, a lone pair sitting on the A, right? So the product of that would be where we have base, the B, being bonded to the hydrogen, and we have the A now with its lone pair all to itself. Now, back to this terminology that we've seen before. A Lewis base having excess electrons and having a negative charge. I say excess being because it wants to get rid of them. The reason that a molecule would ever act as a Lewis base is if it wants to get rid of its electrons, if it has excess electrons. So the fact that this is the base and wants to donate the electrons mean that it has excess electrons. It's got a negative charge. It's going to be the nucleophile. It is the lover of nuclei, or a lover of positive charge. Okay. So we are going to use those terms largely interchangeably. A Lewis base is a nucleophile. Along those same lines, if the acid, HA, is accepting the electrons, it's a electrophile. It is a lover of electrons. It wants those electrons, essentially. So the Lewis acid is an electrophile, a lover of electrons, lover of negative charge. So again, we're going to use those terms interchangeably. Notice in this reaction, we are not only changing the bonding, we're not only making a bond from B to H and breaking a bond from H to A, we are also moving the negative charge. We are actually transferring that negative charge from the B to the A. So in order for this reaction to want to happen, in order for the products to be better than the reactants, in order for the products to be more stable than the reactants, A should be happier with the negative charge than B, and B should be happier with a neutral charge than A. So if A is happier with the negative charge than B, it would make sense that A would be the electrophile. And if B is happier with a neutral charge than a positive charge, it would make sense why we would call it a nucleophile. It would rather be more positive than more negative, and A would rather be more negative than more positive. So any reaction between a Lewis base, a nucleophile, and a Lewis acid, an electrophile, should make a bond. Okay. It might also simultaneously break a bond, like it does here. That's okay too. So in this reaction, since we are making a bond to hydrogen, that hydrogen has to lose its existing bond. That's fine. In this reaction down here, hydrogen does not have a bond yet. It's just H+. So by the base donating to the acid, we are allowed to break a bond without needing to simultaneously make a bond. Okay. Now again, the base in this reaction is getting more positive, going from negative to neutral. So it would make sense that the nucleophile gets more neutral. Also, the acid is getting more negative. The electrophile is getting more negative, going from positive to neutral. Here are a couple more examples of other Lewis acid-base reactions. And we're already moving away from the acid-base notation and defaulting to the nucleophile electrophile notation. The nucleophile is always going to be the Lewis base. Again, those are interchangeable terms. So you're never going to need to figure out if a nucleophile is a base or an acid. It's always going to be the base. But notice that if you compare the reactants to the products, you can see where the bond formation is happening. You can see where bonds are being formed in this top reaction. In these other reactions, we can see where bonds are being broken, okay? So if you ignore this red arrow for a moment and just look at the reactants versus the products, the difference between the reactants and the products is that the nitrogen is bonded to the boron. How in the world would the nitrogen make a bond to the boron? Boron doesn't have any electrons to play with. It only has 6 electrons with it. So the only source of the electrons that we're going to make a bond with must come from the nitrogen. So nitrogen is going to donate its lone pair to the boron. We make a bond. That means nitrogen, NH3, is the nucleophile, and boron and BF3 is the electrophile. Looking at reaction 2, comparing the reactants to the products. Again, you can ignore these red arrows for a moment. If you ignore these red arrows for a moment and only pay attention to what is changing between the reactants and the products, you'll find that we are making a bond between the oxygen and the carbon. So looking here, carbon does not have any electrons available to it to make a bond with. This oxygen, however, has 3 non-bonded pairs of electrons that it can make a bond with. So where are the electrons going to come from? They're going to come from the oxygen. So oxygen will donate its electrons to the carbon. That makes this bond. Now, carbon already has 4 bonds. So if we're going to make a 5th bond to it, we have to simultaneously lose one of the existing bonds. So a question would be, why do we lose the chlorine bond? Why is it the chlorine that detaches in order to make room for the oxygen instead of the hydrogen? Well, this is based on electronegativity again. Notice that when this bond breaks, the electrons go on to the chlorine. So that atom, whichever atom detaches, is getting an additional pair of electrons, and as a result, it's gaining 1 electron more than it had when it was bonded, meaning it's going to have a negative charge. So between the hydrogens and the chlorine, which one is happier with a negative charge? Well, it's chlorine. So chlorine is more willing to detach itself and take the electrons with it than hydrogen is, which is why the chlorine comes off and not the hydrogens. So that's why we have bonds being formed from the O to the C and why the chlorine comes off. Same idea here. In this reaction, again, if we compare reactants to products, the nitrogen is becoming attached to a hydrogen, and the hydrogen is getting detached from its oxygen. So we need to make a bond from the nitrogen, which has a lone pair available to it, to the hydrogen. And since that hydrogen can only make one bond, it has to lose its existing bond to whatever else is attached to it. So the oxygen gains that pair of electrons as a lone pair. Now, that gets us nitrogen with 4 bonds. That's fine. It has a positive charge. That also gets us oxygen with 1 bond and 3 lone pairs, a negative charge. So our charge is still balanced. Again, this is acetate. This is acetic acid. So this is acetate, and we have a resonance stabilized conjugate base. We could delocalize the electrons from this O onto that O. You can see the corresponding electron density if we look at these electron potential maps. On NH3, most of the electron density lies at the nitrogen. This is something you've seen before. I know that we've gone over NH3 when we looked at dipoles and polarity and saw that most of the electron density is on the nitrogen at the site of the lone pair. Now on BF3, remember that the fluorines are very, very electronegative. So they're going to have lots of electron density around them, but they're also pulling electron density away from that boron. So the boron should have large positive character. That's what we see here. That blue area is basically the surface of the very positive boron. So this reaction, even though you know what the product looks like, we're showing you what the product looks like, and so it's easy to conclude, yes, that the nitrogen is donating electrons to the boron. Why does it do that? Why does the nitrogen choose the boron? Why doesn't the nitrogen choose the fluorine, for example? Well, if you think about where the electron density is located, the negative portion of NH3, the nitrogen, is going to be attracted to the positive portion of BF3, which is the boron. So these two pieces right here are going to be most attracted to one another, and that's where we get bond formation. This notation that we've been using is called the curved arrow formalism. What we're doing again is we are simply tracking, we are bookkeeping, we're simply following the flow of electron movement in order to turn the reactants into the products. Okay? So it's used to show the flow of electron pair from the donor to the acceptor. You'll notice in all of these reactions that each pair of electrons gets its own arrow. So the pair of electrons from the O to the carbon gets its arrow, and the pair of electrons from the bond to the chlorine gets its own arrow. Okay. For all of these reactions, you will notice that all arrows are moving in the same direction. They go head to tail. Okay. All of the electrons are moving from left to right in this case, from head to tail. Okay. Standard notation will use a single-headed arrow, or what we said I showed you before was a fishhook, to indicate single electron movement or movement of a radical. And we'll use a standard, I guess you'd call it a double-headed arrow, a standard arrow to indicate that 2 electrons are being moved, a pair. That's called the curved arrow formalism. You can practice, I have this slide here, to practice some aspects of Lewis acid, Lewis base chemistry. What I want you to do is to analyze each of these 3 reactions and figure out which one is the Lewis acid, the electrophile, And which one is the Lewis base, the nucleophile? Like we did before, look at what is changing. Try to identify what bonds are being formed, what bonds are being broken, and try to figure out how are those bonds being formed? How are those bonds being broken? Where are the electrons coming from? That'll help you figure out where the Lewis acid is and where the Lewis base is. I want you to use the curved arrow formalism to show the flow of those electrons, show the electrons moving from the nucleophile to the electrophile, okay? Show any bonds being broken or bonds being formed using those arrows. And if you can, do your best to draw any resonance structures for these charged species. Okay, so show how you might be able to move those charges around. You can pause the video and work on that now if you want. Again, as before, I will have answers to this when we meet next. They'll post those online so you can check them in your own time if you want. But now, do your best to try to practice. If you run into problems, make a note of it. Okay, write down what your question is so that I can help you or your TA can help you when we meet again. Now, one last thing before we go, I want to mention using line angle formula along with resonance. Now, it's okay if you start out using the explicit formulas like the book is using at this point. That's okay. When you're a beginner in organic chemistry, it's important to pay attention to where every atom is, to know where every pair of electrons is. But eventually, you're going to want to move into writing all of your structures in line angle formula because that is a lot quicker. It's a lot simpler at the end of the day. It's a lot simpler. And again, it's kind of the industry standard. So what I just want to show you an example here. If you look at this molecule, this is a pure line angle structure. If you were to expand this structure, you need to figure out where the hydrogens would be. Now, remember that in line angle formula, the idea is that there are as many hydrogens on a carbon as there needs to be in order to fill that carbon's valence. For example, looking at this carbon right here, there are 3 bonds drawn to it. The double bond is 2 and the single bond is 1. That's 3 bonds and the carbon is neutral. There's no charge on it. So neutral carbon has 4 bonds, not 3. So there must be one other bond there that we're not drawing, and that is indeed a hydrogen. Okay. This carbon up here, okay, at the end of this line, there's a carbon there. So how many bonds are drawn to it? Well, 1 bond is drawn. That's all that we have. It's also neutral. So there must be 3 more bonds to it in order to give it 4. That means there are 3 hydrogens there. What's tricky, the trickiest part of this, is the charge. That charge is supposed to represent that it's on this carbon right here. Now, you should know at this point that a carbon with a negative charge has 3 bonds and a lone pair. So we have 3 bonds drawn to this, right? 1, 2, 3. 3 bonds drawn to this carbon. So there must be a lone pair on this carbon. In order for that carbon to be negative, there must be a lone pair. Okay? So we can move that lone pair around. That's what I'm doing here. I'm moving that lone pair around. And every time I move that lone pair, I make a new bond, which means that the other carbon that gets that bond needs to lose an existing bond as a lone pair. So what you might want to do, this might be a good thing to practice, is translate all of these structures from line angle into a full Lewis structure. Draw in all the carbons, draw in all the hydrogens, and follow the charge around. Follow the lone pair around. I'm showing you the movement of those lone pairs. I'm not drawing the lone pairs, but I'm showing you the movement of them. Instead of the lone pair, I'm using a negative charge to indicate where the lone pair is. Okay. And remember, since this is resonance, we're not allowed to move atoms around. So whatever atoms are attached to each other in one structure, all the other atoms are still attached the same way in all the other structures. In this first structure, I'm moving a negative charge around. I'm moving a lone pair around. In this bottom structure, I'm moving bonded pairs around to fix a positive charge. So do your best with that. If you have any questions or you run into problems, check your book, see if your book has any hints. Talk to your fellow students, talk to your TA. I'll do my best to answer any questions that you might have. That's the end of chapter 1. As we said at the beginning of lecture 1, chapter 1 was split into 2 parts, where the first part was a lot of review from general chemistry, and the second half of chapter 1 was what we did today. So we will have a problem set that we will do in class that will be due on Wednesday. These Stromanus chapters, the workshop portion, there's a lot to this chapter. Chapter 4, models 8, 10, and 12. Chapter 5, models 2, 3, 4, 6, 7, and 8. And chapter 2, if you have enough time, which you should have, chapter 2 is, I think it's mostly resonance and bonding. So make sure you work through these. These are, again, very important to understanding and kind of solidifying the information that you learned in this lecture.